All right, good morning, class. Happy Monday. It's September 28th, 2020. Reminders, please get the lab safety contract signed. This is another contract that will apply if we go back to school in the new building later in the year, hopefully. And then there will be an open notes quiz tomorrow, which will cover material from last week. And that will run about 30 minutes tomorrow. AP Classroom has the homework for tonight. And Mastering Chemistry, there's a new assignment, Homework 3, which is going to be due Sunday at 11 p.m. And then study for the quiz. If you have not watched all of the AP Classroom videos for Unit 1 yet, you can continue to watch those as well and take notes. Okay, so the opener for today, if you have this data for copper, these isotopes and these abundances, what would you see on the mass spectrum of copper? And it asks you to make a sketch. So if you take a look, if we have these abundances, let me go to my pen, and here's our mass spectrometer again. So what we would expect to see, I'm going to put some numbers here. So if we make this 20%, this is 40%, 60%, 80%, 100%. And here the mass numbers, I have 63 and 65. So maybe I'll start this off at 62, 63, 64, and 65. Let me just put 66 on there for good measure. I would expect to see at 63 about 69%. So we'd see a peak here that goes up to about, I'm going to pretend that hits like around 70 here. 69 is pretty close to, so that would be the abundance for copper 63. And then at 65, we would see about 30%. So another peak right here like that. And that would be the max spectrum that we would expect for these two main natural isotopes of copper. Okay, let's see here. We're going to go on to the next one. Let me change my pen color. Maybe I can change my pen color. Maybe not. Okay, maybe I'm stuck with red today. All right, so I just wanted to, going back here. Okay, maybe not. Let me just change my pen color if I can to, we'll go with blue today. Okay, so I also wanted to go back and answer Justin's question about like exactly how does the charge to mass race, the mass to charge ratio, how does the magnet affect this? So depending on your charge, of course, you will accelerate faster through the plates. But then if your particles are charged more highly, they will have bigger curvature when they go through the magnetic field here. So it will definitely give you different spots over here on the detector as the particles hit the detector. Now, the reason why this is not as big, I mean, this definitely causes some noise in your signals and more peaks because of the different charges on your ions. But in general, when you ionize a sample of something, there is something called the ionization cross-section. It's kind of a probability of how highly ionized you can make a particle. And so the probability for ionizing something once usually is much greater than ionizing it twice. So most of the particles will go through and get ionized the same way. There will be some that will not because there is some probability of them getting ionized twice or 3 times or 4 times, so forth. And so those will cause peaks in your mass spectrum. When we draw mass spectrums and we see them in AP Chem, they're very much theoretical, ideal spectrums. Real mass spectrums will have like extra peaks. They will be very noisy along the baseline. right? And it's part of a scientist's job to analyze the data and to figure out what the actual signals are telling you. What is the relevant data in the messy spectrum that you see? So hopefully that kind of answers questions about the mass to charge ratio and how that affects the signals that we see here. All right, going on. All right, maybe okay. So this is another kind of mass spec which is very commonly used, especially in pharmaceuticals. Basically, you put some sample right here. They heat it up and it starts vaporizing. Ions are formed as it's shot by a laser. There are different ways to ionize and to vaporize these samples. And then there are accelerating plates, just like before. And then there is this drift tube. They're quite long. Usually time of flight mass specs are about a couple meters long. And so as they move along the drift tube, the ions spread out according to mass. And then the detector picks them up and records the time that the ions appear. And then you get signals, right? You start getting, like, let's say this is 1 second, 2 seconds, 3 seconds, right? You start getting particles built up at certain times along, and if they're right, you can get more signals at certain times if there are more of those ions arriving at the same time because they have a similar mass. So I just wanted to show that just because it is a instrument that people use a lot these days. Okay, my tablet pen does not want to advance. Okay, so we're going to go into 1.3 now, which is the elemental composition of pure substances, basically empirical and molecular formulas. Okay, so here we have empirical formulas, which are the lowest whole number ratio. And then we have molecular formulas, which are not necessarily the lowest whole number ratio. It could be, but the molecular formula actually shows what the molecules in the substance look like, the formula of the molecules. So for example here, what's the empirical formula of H2O2? Well, this is not the smallest whole number ratio, the lowest whole number ratio. We could reduce these and the empirical formula would be HO. Ho, ho, ho. Santa Claus's, well, this is a non-existent molecule, so let's not go there. So it says, is H2O2 an empirical or molecular formula? So since it is not the lowest whole number ratio, this is a molecular formula. All right. It says next ones. What's the empirical formula of glucose? Well, again, here, this is not the lowest whole number ratio. I can divide each of these numbers by 6 and get 1, 2, 1 here. So I would get an empirical formula of CHO. Okay. So then, oops. Next one says, what's the empirical formula of NaCl? Well, this is the lowest whole number ratio. So in this case, the molecular formula is exactly the same as the empirical formula. And that certainly can happen. That can happen many times. All right, so I'm going to go through a couple examples, and then you will be working on some problems on Pear Deck, which I'm trying for the first time. And you will enter your answers in Pear Deck and upload your work to Google Classroom. So this first example, we have a 100-gram sample, and it tells you how many grams of each thing it contains. And it asks, does the empirical formula of the compound lead you to believe it is sodium sulfite? Okay, so if we remember our formulas, sodium ion, okay, this is a ionic compound, metal, and a polyatomic. So we have Na2SO3 is sodium sulfite. or is it sodium sulfate? Okay, different formulas. One has more oxygen. So you got to take this data and turn it into something that has a formula, right? So if we look at a formula, what do these little numbers mean here? There's a 1 here, right? There's a 1 here, but we don't write the ones, okay? But what do these numbers mean? Well, these are the mole ratios, right? They are the ion ratio as well as the mole ratio. So if we can turn these grams into moles, we should be able to write a formula. So the way we do this is we're going to start off with 36.5 grams of Na, and I'm going to divide by the molar mass. Okay, so I'm going to go 1 mole Na is 22.99 grams. And I'm going to find the moles on my calculator. Okay, and that gives me 1.587-ish, 76. I'm going to keep a couple extra sig figs for now, and that gives me the moles of Na. All right, now I do the same thing with my sulfur. 25.4 grams sulfur, okay, times 1 mole S is 32.06 grams. And I divide that out, 0.4 divided by 32.06, and I get 0.7923 moles of sulfur. Okay, last one, I have oxygen, so 38.1 grams of oxygen, okay, times 1 mole oxygen is 16 grams, 16.00. So 38.1 divided by 16. That gives me 2.3813 moles of oxygen. All right, so now I have moles, but these are not whole numbers. So the way we get whole numbers, I look at all 3 moles and I pick which one's the smaller. The smallest one is this one. This is the smallest number of moles. Okay. And I divide by the smallest number of moles for each of these. So I divide by 0.793 here, 0.7923 here, and 0.7923 here. And when I do this, now when I divide through, I get something very close to, put a little squiggly, 2. Okay, 2 moles Na. This is, of course, going to be 1 exactly, 1 mole Na. And this is equal to 3 moles, about 3 moles N of O. All right, oh, sorry, this should not be Na. This should be sulfur. Okay, so then I put these numbers together into a formula. So this is Na2S1, oxygen 3. So this is sodium sulfite, 3 oxygens. Okay, so that's how we get our empirical formula. We're going to do another example. Here's example 2. All right, now this time they give us percentages, not grams. But this is not a problem, okay? To determine the empirical formula of this compound, we are going to imagine, because we have great power with our brains, that we have 100 grams of this compound. Okay, so if it doesn't give you the grams, but gives you percentages, just imagine that you have 100 grams. Now we know that we have 54.53 grams of carbon. Okay, we have 9.15 grams of hydrogen. And we have 36.32 grams of oxygen. It's like magic, you know, the grams just appear we're now going to divide by the molar masses here to get our mole ratios. So this would be 1.8. Okay, this is 1 mole is going to be 16.00 grams. Okay, so I divide these all out by their molar masses. And for carbon, we get 4.515 moles of carbon. I'm getting for my hydrogen 9.077 moles of hydrogen. And last one, divide by 16, I'm getting 2.27 moles of oxygen. Which of these is the smallest? Well, it's the oxygen moles, right? This is the smallest. So I want to get my whole number ratios by dividing by the smallest number of moles, which is 2.27. So this comes out to about, I'm going to put in some actual numbers here. This one, of course, is 1 mole of oxygen. This 4.515 divided by 2.27 is coming right out to about 1.9889. So this is 2 moles of carbon. Okay, and then this one is coming out to right around 3.9987. Okay, so this is about 4 moles, or this is 4 moles of hydrogen. So now take these mole numbers and we'll write a formula, C2H4O. That's our empirical formula. Our lowest whole number ratio. Now, for the molecular formula, it tells us that we have a molecular mass of 132. Well, if I add up the masses here, I'm going to do a rough molar mass count. So 2 times 12. Okay, so we got 24 plus 4 plus 16. That's going to give us about 44 grams per mole. This is clearly not the same molar mass as the molar mass of the molecular formula. So if I take 132 and I divide by 44, I don't really need to do this in my head, but I get 3. Okay, so this means that the molecular formula is 3 times the empirical formula. So the molecular formula is 3 times C2H4. Okay, it needs 3 times the mass of everything in there. So our molecular formula is C6, right? 3 times 2 is 6. H12, 3 times 4 is 12. O3, 3 times 1 is 3. So this is our molecular formula. Okay, so there's our molecular formula, and here's our empirical formula, and we're all set with that. All right, so here's our next question, our third example. So we have this acid-base indicator. Again, here we've got the percentages, so I will just imagine, okay, that I have this 100 grams. I'm going to take 100 grams of this acid-base indicator, and we have a molecular weight, and it asks for the molecular formula. So we know that before we can get to the molecular formula, okay, we have to get the empirical formula. Now, I'm going to show you a little trick. There's another way to do it. Let me see how, in this example where they are doing it exactly the way that they did the I did the previous example too. Now let me go back. Another way I could do this is if I know that the molecular weight is 318, if I know that 75.46% of that has to be carbon. So if I do this 7546, I just changed my and let me call this carbon. And I multiply that by 318 grams per mole, 0.7546 times 318. I get 239. I'll keep a couple extra sig figs grams per mole. I know that this has to be carbon. So if I divide this by 12.01, okay, I will get, it says it's giving me about 19.98 grams. Sorry. We don't have units now because I forgot to put my units here and cancel them. We are getting this many carbons, okay? This is very close to 20 carbons. All right, so now I have my carbon, my hydrogen. I can again change that to a decimal, 443 times 318 grams per mole, 0.0443 times 318. Okay, I'm getting 14.0874. Oops. Uh-oh. Uh-oh. Let me see if I can go back here. I did not mean to erase that. Command Z. Yikes. Okay. Okay, I guess I will just have to go back. We knew that we had 20 carbons. Okay. And then the hydrogen, we were in the midst of taking 14.0874 and dividing this by 1.008. And I'm getting 13.975595, so on. And this is the number of hydrogens. So this is going to be 14 hydrogens. Okay, and then my oxygen point, okay, 0.2010 times 318 grams per mole. Okay, gives me 63.9. So then I divide this by my 16.00, and I get 3.994, but this is very close to 4 oxygen. So taking these numbers, get C20. Oh, let me rewrite that because that does not look good. C20, H14, O4. And hopefully that is the same thing that we've gotten in the next slide. Yeah, and it is. So you can see we could do the same thing. Now, I'd like you to look at this solution. In fact, in class, probably, I will ask you to do this. And the reason why is when you divide these out, you'll get numbers, but look at this number. This is not a whole number. It's 3.5. So when you get numbers that are not whole numbers, you need to multiply by a factor to get them to be whole numbers. And then you can get the correct ratio here. Now, if this question had asked for the empirical formula, you'd have to either do this and then go backwards to the empirical formula, but you would do this to get the empirical formula here. So this would be the empirical formula. Okay. All right, so then you guys will be doing 2 pair deck problems on this to make sure that you're able to do this. Here's a hydrate problem, and then we will go into this POGIL. You will work together on the POGIL on this, and then I'll be collecting your papers on Google Classroom. And then we'll go into this problem. So here, after you do the combustion analysis, this is going to make a lot more sense because it'll review what combustion is. So it says that you're completely combusting a hydrocarbon. So a hydrocarbon contains some carbon, well, some amount of carbon, we'll just call it X, and HY. Okay, so if we take a look here, we see that we're getting 1, 2, 3, 4, 5, 6, 7, 8 H2Os. So let me write those as products. So we've got 2 products here, H2O plus 1, 2, 3, 4 CO2s. And we need to go over here. We always know that combustion involves oxygen, so let's put the oxygen in. And then we have to figure out what over here is going to balance these amounts of water and carbon dioxide. So if I look at the carbon dioxide first, I see that I have 4 carbons. So I'm going to put C4 here. And then my H, I see that I have a total of 16 H's over here, 8 times 2. So here's C4H16. So, however, be careful. They're asking for the empirical formula. So the empirical formula of this, if we divide both of the 4 and the 16 by 4, we get CH4. Okay? So CH4 is the actual, probably the actual compound. But this is the question they're asking. And this is the answer for the empirical formula. Okay. So then I show you this apparatus. Again, these apparatuses, you know, I think a lot of times people want to know, like, oh, how does this actually look? So here's the combustion analysis apparatus. We have our combustion tube that burns up the stuff. Here's the furnace, right? It goes through and it makes a lot of gases, CO2 and H2O. And so you go along here, it collects all the, in this anhydrous part, like they're showing it a little blow up right down here, like magnesium perchlorate is a very hygroscopic absorber. So it will absorb the water vapor coming off from the furnace. And then you can weigh this afterwards to see how much water was absorbed. And then over here, we have another absorber. So NaOH, some strong base will absorb the CO2. And then any other gases come out of the combustion analysis. So that's the basic operation of a combustion analysis apparatus. So here's the basic procedure, okay? We get the mass of the compound to be combusted. We need the mass that we're burning up. We figure out how much water is produced, how much CO2 is produced. Then whatever's left over that's not accounted for in the mass by these two, by the water and the carbon dioxide, the oxygen is what's left over. Okay, so we have some compound like this. Now, some compounds may also contain nitrogen. Okay, but the problem will make that clear to you. Okay, so it will tell you what things are in the compound. All right, so here's an example problem, and then you guys are going to tackle one of these combustion analysis problems. So let's go and take a look. We have, here's our sample mass, here's our total mass. Okay, and we're going to produce this much CO2 and this much H2O. And it's asking, what's the empirical formula for menthol? We'll probably just stop at that part because once you find the empirical formula, the procedure for finding the molecular formula is exactly the same in this problem. So I'm going to start off with my CO2. So in your combustion analysis prep, it's kind of prepared you for how to get the carbon out of the CO2. So this is the grams of carbon dioxide. I'm going to change that to moles. You can also use a percent composition for this part if you want. So that's 44.01 grams. It will give you exact same answer. And then I know that there is 1 mole of carbon in every 1 mole of CO2. And so that will give me 12.01 grams per 1 mole of carbon. This is going to give me my grams of carbon. So I'm going to go here, 0.2829 divided by 44.01 times 12.01. Okay, and I get 0.07720 grams of carbon. Okay, so I know that that many grams of carbon are produced based on the CO2 that comes out. Now I'm going to do the same thing with my H2O. 59 grams H2O, 1 mole H2O is 18.02 grams times 1 mole. Sorry, we're getting 2 moles H for every 1 mole H2O. Okay, and then times 1.008 grams for 1 mole H. Okay, so let's multiply this out. Divided by times 2 times 8. And I'm getting 0.0129. Let's say we'll just carry a couple extra grams of hydrogen. So the carbon and the hydrogen make up this much mass. The total sample is this. So let's subtract off to get the grams of oxygen. We're going to take the total grams minus the carbon grams minus the hydrogen, 2966 grams of hydrogen. So multiplying it, no, subtracting from 0.1005 and then subtracting off the carbon, I'm getting that my grams of oxygen left is 0.01033 grams of oxygen. So this is, so far, this is what we have. Now to get my empirical formula, I change those into moles. Okay, so 20 grams of carbon. Okay, I'm going to multiply, sorry, not multiply, but divide by my molar mass to get to moles of carbon. So 0.07720 divided by 12.01, I get 0.006427.9. Well, thank you, so on. So this is my moles of carbon. My hydrogen, again, I'm going to divide by the molar mass. Try not to hit my erase button. Would be a shame. And we get 0.012863 moles of H. And then my oxygen, 0.01033 grams of oxygen, 1 mole O, 16 grams, 0.01033 divided by 16. I'm getting 0.0006456 moles of oxygen. So which one's the smallest? Well, it looks like this one. So I divide all of the moles of oxygen are the smallest. So, and I'm missing a 0 here, 3 zeros. That's going to give us 1 mole of oxygen. If I divide 0.0006456. Okay, I take my current moles of carbon, divide it out, I get something like 9.956. This is very close to 10 moles of carbon. And then this amount of hydrogen divided by the smallest number of moles, 863 divided by 0.0006456. I'm getting 19.924. This is close to 20 moles of hydrogen. Okay, so we take these, our empirical formula is C10H20O. So that's our formula for menthol. And then if we want to check our molar mass, we can do a quick check here. 120 plus 20 plus 16. Well, that looks like it. That's giving us 156. So this is also the molecular formula because the molar mass of the empirical formula is the same as the molar mass of the molecular formula. Okay, so that's our combustion analysis example there. So I would highly recommend that you hopefully you've kind of processed this and you've taken the notes of what we just did in your notebook. Think about what steps we took to solve this combustion analysis problem, so that it's clear in your head, you know, like if I see this type of problem, I know I need to do this to change it into that and then do that. So make sure those steps are clear in your head. Okay, so then you guys will do a couple problems on combustion analysis, one on benzoic acid, and then one on gasoline. This is the answer that you will get for the second one. And I just want to take this and I'm going to draw this a slightly different way. So organic chemists, and this is going to come up in Mastering Chemistry, number 17 in homework 3. And I was alerted to this by a student because they were confused. And if I take this and I do something which is called a skeletal form or structure, the skeletal structure, organic chemists, okay, instead of drawing this all out, they might write it like this. And basically, you probably look at this and say, oh, man, that's like just a bunch of weird just lines. What you have to know is that where lines intersect, that's a carbon. Okay. And where lines end like this, that is a carbon with 3 hydrogens. This carbon has 0 hydrogens. because it already has 4 other carbons attached to it. So if you see something like this, it does not mean there's nothing here. This intersection where the lines intersect is a carbon. So in this case, the carbon is attached to 3 hydrogens, and those are shown explicitly here, because if I did not put the hydrogen in, then it would count as a carbon with 3 hydrogens. And so this carbon is attached to 1, 2, 3 hydrogens and an OH group. So the formula for this would be CH3OH. For this right here, we have this formula, the C5H12O. So hopefully that clears up any confusions about if you see these structures. Okay. So another problem that you're going to do, hopefully, and here is the solution to that one right there. And yeah, more solution part for the hydrates. The hydrates, remember, we have the ionic part. So, and then we have the water part. Okay, so if we take a look here from the anhydrate, we have Fe NO2, 3, and then we have 4 waters based on the ratios of the ionic, the anhydrate, and the water. Okay, so there are just 2 components to this problem is a little more complicated because they have you figure out the empirical formula as well for the anhydrate, for the ionic part. But it's exactly the same. Okay, so here we have a diagram representing some elements from a decomposition of a compound. It says that blue is nitrogen. Okay, so this thing is N2, and this is oxygen. And they want the empirical formula of the original compound. So again, here I would write out the products, okay? So decomposition means that we had something and it decomposed into 1, 2, 3 nitrogens. And 1, 2, 3, 4, 5, 6 oxygens. All right, so if we go back and write the formula, we have a total of 6 nitrogens, so N6. Okay, and we have 12 oxygens, so O12. What's the empirical formula, though? Well, divide both of these by 6, and we should get that for the answer, which I believe I have on the next page, right here. So this is our empirical formula. There's no way we can figure out the molecular formula, right? Because we just know the ratio of the products that was formed. We don't know whether the product originally formed was, sorry, the reactant that it came from was 2 times this, 3 times this, 6 times, 10 times, 100 times. We can only know the simplest whole number ratio of the original compound. Okay, so if we go into 1.4, and I need to add a little section header for this. We want to figure out if we get 10 grams of some white solid, we want to figure out whether it's regular table salt or salt substitute. So I'm going to have you guys discuss this, but if you think about sodium chloride, NaCl, and something like KCl mixed into it, how do we know that this is not just plain salt, pure salt, or if it's a salt substitute which has NaCl and KCl mixed. So you're going to discuss this, but basically the clue is the Cl. The amount of Cl in a mixture will be different than if something was completely pure. The reason is because the masses of Na and K are different, right? So if we have 10 grams of pure salt, right, the mass of Cl that combines with the sodium is a certain amount. But if some of that 10 grams is potassium, right, potassium has a bigger mass. It combines with the same amount of Cl, but K is going to take up more of the mass of the 10 grams. So we're actually going to have less Cl in here than expected, okay, for a pure sample of sodium chloride. I hope that makes sense. So here I'm kind of walking you through what's going on. Like, think about how many moles of Cl you'll get if you have pure NaCl, but then if you have part NaCl and parts KCl, think about how many moles of Cl you get. And then think about what weighs more. Okay, and then going over the answer there. And then you are going to discuss and choose an option for that problem on Pear Deck. The answer is D, by the way. And then over here, another discussion question about how you could figure out whether the paprika was spiked with lead oxide. Ooh, the things people do to cut cost and to reduce the amount of I suppose just, I don't know, cut costs and make more profit. So, okay. And then I think that comes to the end of part 1. And that would hopefully take class 1. And then we would go into atomic structure and electron configuration here.